Welcome to Ultimate Sleep Doctor. Tonight, we'll explore a realm beyond our everyday understanding. Quantum physics whispers of realities far stranger than we can readily perceive, a universe where particles exist in multiple states simultaneously, where observation shapes existence itself. It's a place where space and time aren't fixed, but probabilities waiting to unfold. Consider the sheer elegance of this hidden world, a reflection of the interconnectedness of all things. Perhaps, in contemplating these mind-bending realities, we find a deeper peace. If you're seeking a gentle exploration of the extraordinary, we invite you to subscribe and share this journey with others. Just breathe. Let your thoughts drift like clouds across a vast, blue sky. Let's begin. The universe, at its most fundamental level, isn't always what it seems. It's a place of incredible surprises, of things behaving in ways that seem to defy our everyday experiences. Before we delve into some of the stranger aspects, let's consider the question of what something is. We're used to thinking of things, a ball, a table, even ourselves, as solid, definite objects. They have a size, a shape, a location, and they behave predictably when we push on them or observe them. But at the quantum level, this comfortable picture starts to crumble. The key to understanding this strange behavior lies in a concept called wave-particle duality. This idea, initially proposed by physicists like Louis de Broglie, suggests that everything from electrons and photons and particles of light to even larger things like atoms and molecules can behave as both a wave and a particle. It's not that something is sometimes a wave and sometimes a particle. It's that it possesses properties of both, and which behavior we observe depends on how we're looking at it, or more precisely, how we're experimenting. For centuries, scientists believed that light, for instance, was made up of tiny particles, little packets of energy called photons. This idea, championed by Isaac Newton, painted a picture of light as a stream of bullets, each carrying a specific amount of energy. However, in the late 19th and early 20th centuries, experiments began to challenge this view. James Clerk Maxwell's equations, describing electromagnetism, predicted that light should behave like a wave, characterized by properties like wavelength and frequency. Experiments confirmed this, showing light diffracting Ella's bending around corners and interfering, combining with itself, behaviors that are hallmarks of waves. It wasn't until the 1920s that the wave-particle duality truly began to solidify. Niels Bohr proposed a revolutionary idea that electrons, previously thought of as tiny, solid particles orbiting the nucleus of an atom, could also behave like waves. This wasn't simply a theoretical musing. It was backed by experimental observations. But the truly mind-bending demonstration of this duality came with the famous double-slit experiment. The double-slit experiment was first conducted with photons, but it was quickly adapted to use electrons. Imagine a barrier with two narrow slits cut into it. Behind this barrier is a screen that detects what passes through the slits. If you send a stream of marbles through the slits, you'd expect to see two distinct bands on the screen, corresponding to the marbles that went straight through each slit. It's a simple, predictable outcome. Now, let's send electrons, one at a time, through the same apparatus. Here's where things get incredibly strange. Instead of two distinct bands, an interference pattern begins to emerge on the screen. This pattern consists of multiple bands of high and low intensity, similar to the interference patterns created when waves overlap. This suggests that each electron is passing through both slits simultaneously and interfering with itself, a behavior completely unlike anything we experience in our everyday world. To understand this, consider wave behavior. When two waves meet, they can either add together constructive interference to create a larger wave, or they can cancel each other out destructive interference to create a smaller wave. The interference pattern on the screen is a direct result of electrons passing through both slits as waves and interfering with each other. Crucially, the electrons don't seem to choose which slit to go through. If you try to observe which slit an electron passes through, for example, by shining light on it, the interference pattern disappears. The very act of observing the electron seems to force it to behave like a particle, going through one slit or the other. This is often referred to as the observer effect, and it highlights the fundamental role that observation plays in quantum mechanics. It's tempting to think of the electron as having a ghostly duplicate, somehow going through both slits at once. However, the nature of this wave is not like a traditional wave. It's not a physical disturbance in a medium like water. Instead, it's a probability wave, a mathematical description of the probability of finding the electron at a particular location. The wave spreads out, and it's the square of the wave's amplitude that represents the probability. Before an electron interacts with a detector screen, it doesn't have a definite position. It exists in a superposition of states, meaning it has a probability of being found at many different locations simultaneously. Only when it interacts with something like a detector screen does this wave collapse, and the electron chooses a specific location. The double-slit experiment and the concept of wave-particle duality challenges our intuitive understanding of reality. It demonstrates that at the quantum level, particles aren't always particles, and they aren't always waves. They exist in a state of probabilistic existence, governed by the laws of quantum mechanics. It's a humbling reminder that the universe, at its most fundamental level, operates in ways that are profoundly different from our everyday experiences. It encourages us to question our assumptions and to appreciate the astonishing strangeness of the cosmos. The universe, as we experience it, often feels like a place of precise measurements. We build our lives around accurate clocks, meticulously calibrated scales, and the certainty of knowing where something is and how fast it's moving. But delve deep enough into the world of quantum physics, and you'll encounter a profound and unsettling truth. There's a fundamental limit to how precisely we can know certain things about the tiniest building blocks of reality. This limitation isn't a technological problem. It's an inherent property of the universe itself. It's a concept famously articulated by Werner Heisenberg, and it's known as the uncertainty principle. At its core, the uncertainty principle states that there's a built-in fuzziness to our ability to simultaneously know both the position and momentum of a quantum particle, like an electron. Let's consider an electron. Momentum, in simple terms, is a measure of how much oomph an object has when it's moving. It's related to its mass and speed. Now, imagine trying to pinpoint the exact location of this electron. You might shine a beam of light photons at it. These photons collide with the electron, and by observing where the electron scatters, you can get an idea of its position. However, the very act of measuring its position disturbs its momentum. Think of it like trying to find a small, slippery ball in a dark room. If you shine a flashlight on it to locate it, the light itself pushes the ball, changing its speed and direction. The more precisely you try to determine where the ball is, the more you've altered its motion. Similarly, when a photon interacts with an electron to determine its position, it imparts momentum to the electron, changing its velocity and, consequently, its momentum. The more accurately you measure the position, the greater the disturbance to the momentum, and vice versa. It's not that our instruments are imperfect. It's not a matter of blurry readings or faulty equipment. The problem lies in the nature of the quantum world itself. Quantum particles don't possess definite values for both position and momentum until they are measured. Before measurement, they exist in a state of probabilistic possibility. described by a wave function. This wave function represents all the possible locations and momenta the particle could have. It's like a cloud of possibilities, rather than a single, defined point. The act of measurement forces the wave function to collapse into a single, definite state, giving the particle a specific position and momentum. But this collapse inherently introduces uncertainty. The more we learn about one aspect, the less we know about the other. It's a trade, oft dictated by the fundamental laws of nature. Mathematically, the uncertainty principle is expressed by an equation tan x or dan p$2, where x represents the uncertainty in position, to p represents the uncertainty in momentum, and as, pronounced bar, is the reduced Planck constant, a tiny number that characterizes the scale of quantum phenomena. This equation simply states that the product of the uncertainties in position and momentum must be greater than or equal to a fixed value. It's not a suggestion, it's a requirement. This isn't just a problem with electrons. It applies to all quantum systems, photons, atoms, and even larger particles like protons and neutrons, though the effects become less noticeable as mass increases. The larger the particle, the more pronounced the uncertainty becomes. But the principle remains. It's important to understand that the uncertainty principle doesn't imply that we can't ever know both position and momentum exactly. It simply means there's a fundamental limit to how accurately we can know them simultaneously. We can reduce one uncertainty at the expense of increasing the other. Consider a scenario involving a tiny, confined particle, like an electron trapped in a very small box. If we confine the electron to a small space, reducing the uncertainty in its position, its momentum will become increasingly uncertain. Conversely, if we allow the electron more freedom of movements, reducing the uncertainty in its momentum, we can't precisely pinpoint its location. The implications of the uncertainty principle extend far beyond the simple example of measuring a single particle. It fundamentally shapes our understanding of the behavior of atoms and molecules, influencing everything from chemical reactions to the stability of matter. It challenges our classical intuitions about the world, reminding us that at the most fundamental level, reality is not deterministic but probabilistic. Scientists have experimentally verified the uncertainty principle countless times, confirming its validity with remarkable precision. These experiments often involve observing the behavior of particles in quantum systems, and the results consistently align with the predictions of the principle. Ultimately, the uncertainty principle isn't a sign of weakness in our measuring abilities. It's a profound and elegant reflection of the nature of reality at its smallest scales. It's a constant reminder that the universe is inherently uncertain, and that our attempts to understand it will always be limited by the very fabric of existence. It is a cornerstone of quantum mechanics, a principle that continues to shape our scientific understanding and challenge our perceptions of space, time, and the very nature of observation. The universe, as we've begun to understand, doesn't operate with the simple, straightforward logic of a clock or a falling stone. It's a place of profound mystery, a place where the rules we're accustomed to simply don't apply. Our journey into the heart of quantum mechanics has already revealed this, unveiling the bizarre nature of particles behaving as both waves and particles, and the frustrating limitations we face when trying to observe them. But now, we're going to explore a connection, a link between particles that's truly astonishing: quantum entanglement. It all began with Albert Einstein's skepticism. He wasn't comfortable with the implications of quantum mechanics, particularly this seemingly instantaneous connection. He famously called it spooky action at a distance. The core of the issue revolves around two particles. Let's call them particle A and particle B. These particles can be created in a way that links their properties in a very specific, fundamental manner. It's not that they've been pre-programmed with a linked fate. Instead, the act of creating them or interacting with them in a particular way establishes this connection. Let's say particle A is a photon, a particle of light, and particle B is another photon. We can create them in a process where their spin is correlated. Spin, in the quantum world, isn't actually about rotation like a spinning top. It's a fundamental property of the particle, a form of angular momentum that behaves as if the particle is spinning. But it's a much more abstract concept. What's important is that when we measure the spin of particle A, we will always find it to be either up or down. And, incredibly, if we instantly measure particle B, no matter how far apart they are, we will always find that its spin is the as opposite. If particle A is up, particle B will be down, and vice versa. This isn't simply a case of us knowing the spin of both particles beforehand. Before we make the measurement, both particles exist in a state of superposition, meaning they simultaneously possess both and down spin. It's only when we observe one that it causes a definite spin, and instantly, the other particle adopts the opposite state. Now, consider the distances involved. We've demonstrated this effect with photons, separated by millimeters, by kilometers, and even by across the globe. The distance doesn't matter. The connection remains instantaneous. This is what deeply troubled Einstein. His theory of special relativity posits that nothing can travel faster than the speed of light. How could particle B instantaneously know what particle A was doing? Across vast stretches of space, without any signal passing between them. It seemed to violate the very fabric of space-time. The key to understanding this isn't to think of it as information being transmitted, because it isn't. It's more accurate to consider that the two particles exist as part of a single, unified quantum state, even when physically separated. Measuring one particle forces the entire system to collapse into a definite state. And because of the initial correlated creation, the other particle instantly assumes the corresponding state. It's like flipping two coins simultaneously and always getting one heads and one tails. Knowing the result of one flip instantly determines the result of the other. But no information was exchanged between them. Scientists have conducted countless experiments to verify this phenomenon, and the results are consistently astonishing. The most famous, and often misunderstood, experiment involves pairs of photons generated through a process called spontaneous parametric down conversion. This process takes a laser beam and through a special crystal, splits it into pairs of photons that are entangled. These entangled photons are then sent in opposite directions, and scientists measure their polarization. Another property related to their orientation at distant locations. The results consistently show correlations exceeding what's possible if the photons were simply carrying pre-determined information. There are fascinating implications stemming from entanglement. One potential application is in quantum computing. Quantum computers harness the principles of superposition and entanglement to perform calculations in ways that are fundamentally different and potentially far more powerful than classical computers. However, building and controlling quantum computers is extraordinarily challenging. Maintaining the delicate quantum states of entangled particles is incredibly sensitive to environmental disturbances. Moreover, entanglement is leading to explorations in the realm of quantum teleportation, not in the way you see in science fiction, where people are instantly transported from one place to another. Instead, quantum teleportation involves transferring the quantum state of one particle to another. The original particle is destroyed in the process, and its state is recreated perfectly at the distant location, utilizing entanglement as the channel. Despite the strangeness, entanglement has become a cornerstone of modern physics. It continues to be a subject of intense research, pushing the boundaries of our understanding of the universe and potentially unlocking new technologies. While Einstein initially resisted its implications, he ultimately accepted its reality, recognizing that it posed a profound challenge to our intuitive notions of space, time, and causality. It reminds us that the universe, at its most fundamental level, operates in ways that are often profoundly counterintuitive to our everyday experiences. The universe, as we generally perceive it, operates on the principle of cause and effect. If you push a ball, it rolls. If you apply force, something moves. But at the smallest scales, the rules begin to shift to become exquisitely strange. Let's consider a simple scenario, a ball rolling towards a wall. Normally, the ball would bounce back, wouldn't it? Its kinetic energy, the energy of motion, would be reflected. But quantum mechanics introduces a remarkable counterintuitive possibility: quantum tunneling. It all began with Niels Bohr, a brilliant Danish physicist who was pondering the behavior of electrons orbiting the nucleus of an atom. He realized that the classical model of an electron orbiting at a specific distance simply couldn't explain the observed stability of atoms. Electrons, according to classical physics, should constantly emit radiation and spiral into the nucleus, yet atoms held together remarkably well. Bohr's solution, initially met with skepticism, suggested that electrons weren't orbiting in neat, predictable paths, but rather existed in regions of space orbitals, where they had a certain probability of being found. These orbitals weren't fixed tracks, but rather fuzzy clouds of potential locations. This probabilistic nature was key to understanding tunneling. The wave-like behavior of particles, as demonstrated in the double-slit experiment, continues to be a cornerstone of quantum mechanics. When a particle, like an electron, is described by a wave function, this function doesn't represent a single, defined location, but rather a distribution of probabilities. It's like casting a stone into a pond. The ripples spread outward, and at any given point, the water has a certain level of displacement. The wave function is similar, indicating the likelihood of finding the particle at a particular spot. Now, let's return to our wall and the electron. If the electron's wave function encounters a barrier, in our case, a wall, it doesn't abruptly stop. Instead, a portion of the wave function penetrates the barrier. This isn't a matter of the electron somehow magically dissolving and reappearing on the other side. It's more accurate to say that the wave function extends into the barrier, diminishing in amplitude, strength as it goes deeper. The probability of finding the particle within the barrier isn't zero, it's a small, but non-zero chance. The thickness and height of the barrier are crucial factors. A thinner, lower barrier offers a greater opportunity for the wave function to tunnel through. The higher the potential energy of the barrier, the energy required to push the particle through, the lower the probability of tunneling. It's like trying to roll a ball up a very steep hill. The steeper the hill, the less likely you are to reach the top. Let's consider a particularly famous experiment that beautifully illustrates this phenomenon: the tunneling of alpha particles through a thin barrier. Alpha particles, emitted during radioactive decay, are relatively massive and possess a significant amount of energy. Classically, they shouldn't be able to penetrate a barrier that's only a few millimeters thick. However, experiments consistently showed that a measurable number of alpha particles did appear on the other side, demonstrating tunneling. The probability of tunneling was incredibly small, but not zero. The mathematics describing tunneling relies heavily on the Schrödinger equation, the fundamental equation of quantum mechanics. Solving the Schrödinger equation for a particle encountering a barrier yields the probability of transmission, the probability that the particle will pass through the barrier entirely. This probability depends on the particle's energy, the barrier's width and height, and the nature of the barrier material. It's important to understand that tunneling doesn't violate the conservation of energy. The particle doesn't gain energy to pass through the barrier. It simply exploits the wave-like nature of its existence to probabilistically borrow energy momentarily, passing through and then returning to its original state. Quantum tunneling has significant practical implications. It's a key component in the operation of the flash memory used in your smartphone and computer. The movement of electrons through the insulating layers of these devices relies on tunneling to store and retrieve data. Moreover, tunneling plays a crucial role in nuclear fusion, the process that powers the sun and other stars. The protons within atomic nuclei overcome the electrostatic repulsion between them through tunneling, allowing them to fuse together and release immense amounts of energy. Furthermore, scientists are actively exploring the potential of tunneling for applications like quantum computing. Tunneling can be used to transmit information between qubits, the basic units of quantum information, offering a way to overcome the limitations of traditional computing. The concept of quantum tunneling is profoundly counterintuitive. It challenges our everyday understanding of how the world works, demonstrating that at the quantum level, reality is far more fluid and probabilistic than we perceive. It's a window into a universe where particles can seemingly defy the constraints of space and energy, highlighting the bizarre and beautiful complexities of the quantum realm. As we continue to probe these mysteries, the more we realize that the universe holds secrets far beyond our everyday comprehension. The world, as we normally perceive it, runs on clear distinctions. A ball is either red or blue. A coin is either heads or tails. A light switch is either on or off. These are simple, unambiguous states, and we build our understanding of the universe on this bedrock of certainty. But delve into the realm of the incredibly tiny, the world of atoms, and the particles that make them up, and this familiar sense of certainty begins to dissolve. It's here, at the heart of quantum physics, that we encounter a concept so strange, so counterintuitive, that it challenges our most basic assumptions about reality: quantum superposition. Superposition isn't about a particle being both red and blue, or possessing both heads and tails simultaneously in the way we might superficially understand. It's far more profound than that. Instead, consider a quantum particle like an electron. Before we attempt to measure its properties, its position, its momentum, its spin, it doesn't have a definite value for any of these. It exists in a state of potential, a blurry blend of all possible states simultaneously. Think of it like a musical note that hasn't been played. It has the was potential to be a high note or a low note, a sharp note or a flat note. It's not that it is one or the other, but that it holds the possibility of becoming either. This potential isn't just a matter of our ignorance. It's a fundamental property of the particle itself. The electron, for example, possesses an intrinsic angular momentum called spin. We describe this spin as being either up or down along a chosen axis. But until we measure the spin, the electron doesn't have a definite spin. It's in a superposition of both up and down states simultaneously. It's as if the electron is rotating, but in every possible direction at once. This isn't about the electron spinning quickly. It's about the fact that it hasn't yet chosen to spin in a specific direction. The mathematics describing this state is elegantly simple, yet profoundly unsettling. We represent the state of a particle in superposition with a mathematical equation. This equation doesn't provide a single, definite value for the particle's property. Instead, it describes the probability of finding the particle in each possible state if we were to make a measurement. The equation essentially says, There's a 50% chance the electron will be up spin and a 50% chance it will be down spin. It's not that it's equally likely, but that the equation formalizes this inherent uncertainty. To understand this a little better, let's consider a famous thought experiment called Schrödinger's cat. This isn't a literal experiment, of course, but a way to illustrate the implications of superposition. A cat is placed in a sealed box along with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, a random event governed by quantum probabilities, the Geiger counter detects it, triggering the release of the poison and the death of the cat. Before we open the box, according to quantum mechanics, the atom exists in a superposition of both decayed and undecayed states. Consequently, the cat, linked to the atom's state, also exists in a superposition of being both alive and dead. It's only when we open the box and observe the cat that the superposition collapses, forcing the cat into one definite state, either alive or dead. The crucial thing to grasp is that the act of measurement, the observation, fundamentally alters the system. Before observation, the particle exists in this hazy realm of possibilities. The moment we try to pinpoint its location or measure its momentum, the superposition collapses, and the particle chooses one definite state. It's not that our observation causes the collapse. Rather, the measurement process itself forces the particle to commit to a single reality. This isn't simply a problem of our limited knowledge. It's a core principle of quantum mechanics, demonstrating that reality at the smallest scales isn't necessarily tied to our perceptions of it. The implications are staggering. It suggests that at the very foundations of the universe, existence isn't always definite until it's observed. Scientists are actively exploring ways to manipulate and control superposition. For instance, researchers are developing technologies based on quantum computing, which harnesses the ability of qubits, quantum bits, to exist in a superposition of 0 and 1 simultaneously, allowing them to perform vastly more complex calculations than classical computers. The potential applications of this technology are enormous, ranging from drug discovery and materials science to cryptography and artificial intelligence. Superposition highlights just how different the quantum world is from our everyday experience. It's a reminder that the universe is far stranger and more wonderful than we might initially imagine. It's a world where possibility reigns supreme until we dare to look, and then reality finally takes shape. As we drift off to sleep, remember that even the smallest pieces of the universe hold secrets beyond our current comprehension, and that the act of observing can change everything. The universe, as we often perceive it, is a stage filled with distinct objects: a rock, a bird, a star. We build our understanding of the world based on these solid, tangible things. But what if that sense of solidity is a beautiful illusion? What if everything we see, everything that exists, isn't actually made of these individual things, but instead arises from a far more fundamental, pervasive source? This is the core idea behind quantum field theory, and it's a concept that paints a truly astonishing picture of reality. At its heart, quantum field theory proposes that space isn't empty. It's not a void, but rather a vast, intricate network of fields, like a gigantic, invisible ocean stretching across all of existence. These aren't fields like the magnetic field around a magnet, which we can easily measure and interact with. These quantum fields are far more subtle, fundamental, and universal. For every type of particle, we know electrons, photons, quarks. There's a corresponding quantum field that permeates all of space. Consider the electromagnetic field, the one responsible for light and magnetism. Within this field, the energy isn't concentrated in a single, discrete location like a tiny ball. Instead, energy exists as ripples, vibrations, or disturbances within the field itself. When enough energy accumulates in a specific region of the field, it manifests as a particle, a photon, the fundamental particle of light. Think of it like dropping a pebble into a still pond. The ripples spread outwards, and those ripples are analogous to the excitations within the electromagnetic field. A large enough disturbance creates a wave, and a smaller, more localized disturbance creates a photon. Now, let's zoom in on electrons. Similarly, the electron isn't a tiny, solid sphere. Instead, it's an excitation, a vibration, within the electron field. It's a localized ripple of energy within this field. The properties of the electron, its mass, its charge, are determined by the characteristics of the underlying electron field. Just as the shape and size of the ripples in the pond determine the wave's amplitude and wavelength, the characteristics of the electron field determine the electron's properties. It gets even more interesting when we consider particles like quarks. Quarks aren't fundamental in the same way as electrons. They themselves are excitations of even deeper fields, the quark fields. These quark fields interact to form the protons and neutrons that make up the nuclei of atoms and, ultimately, the atoms that make up everything we see. The entire structure of matter, from the smallest subatomic particles to the largest galaxies, can be understood as patterns of excitation within these underlying quantum fields. A crucial aspect of this theory is that particles aren't created and destroyed. They are merely transformed from one state of excitation to another within a quantum field. Imagine a guitar string vibrating. It can create different notes depending on the frequency of the vibration. Similarly, a quantum particle can transition between different energy levels or states within its corresponding field, effectively appearing to disappear and then reappear as a different particle. This isn't about particles moving through space. It's about the rearrangement of energy within the fields themselves. The mathematics describing quantum field theory is incredibly complex, relying heavily on concepts like quantum operators and field operators. These mathematical tools allow physicists to precisely calculate the probabilities of different transitions and interactions within these fields. They also provide a framework for understanding phenomena like particle creation in particle accelerators, where high-energy collisions create new particles by briefly distorting and then re-forming the quantum fields. Furthermore, quantum field theory provides a compelling explanation for the vacuum of space. It's not truly empty. It's teeming with virtual particles constantly popping into and out of existence. These fleeting particles, like photons and electrons, are temporary excitations within the quantum fields, allowed by the uncertainty principle. They exist for an incredibly short time before annihilating each other, but their constant presence contributes to the overall energy density of space. The beauty of quantum field theory is its elegance and predictive power. It successfully explains a vast range of phenomena, from the behavior of elementary particles to the structure of the universe. It's also the foundation for the standard model of particle physics, our current best description of the fundamental forces and particles in the universe. It's important to grasp that this isn't just a theoretical concept, it's a description of reality itself. We're not just observing particles, we are experiencing them as manifestations of these underlying fields. Our own bodies, our thoughts, our very existence, are ultimately rooted in the interactions within these vast, invisible networks of energy. As you drift off to sleep, consider the profound implications of this idea, that the universe, in its most fundamental form, is a symphony of vibrations within these timeless quantum fields. The universe, as we typically understand it, operates on a scale of vast distances and predictable laws. Gravity governs the swirling dance of galaxies. Electromagnetism dictates the behavior of light, and the strong and weak nuclear forces hold the very fabric of atoms together. But what happens when we zoom in? Not just to the incredibly small, the realm explored in Part 4 with quantum tunneling, but to the unimaginably tiny scales of subatomic particles. It's here, at the heart of quantum mechanics, that things begin to unravel, to present realities that defy our everyday intuitions. We've explored superposition, the idea of a particle existing in multiple states at once, and the strange possibility of particles seemingly appearing and disappearing, driven by the underlying quantum fields described in Part 6. But a truly mind-bending consequence of quantum mechanics arises when we consider what happens during a measurement. The very act of observing a quantum system seems to fundamentally alter it. This is where the many worlds interpretation, often shortened to MWI, comes into play. It wasn't born from a single, dramatic aha moment, but rather grew from decades of wrestling with the seemingly paradoxical nature of quantum measurement. The core problem, as it was seen by physicist Hugh Everett III in 1957, was the wave function collapse. The wave function, a mathematical description of a quantum system, evolves smoothly and predictably according to the Schrödinger equation. This equation describes the probability of finding a particle in a particular state. However, when we measure a particle, the wave function suddenly collapses into a single, definite state. Before the measurement, the particle was in a superposition of all possible states. After the measurement, it's definitively in one. The question then becomes, what causes this collapse? Why doesn't the wave function continue to evolve smoothly, even when we're observing it? The standard interpretation, the Copenhagen interpretation, simply postulates that collapse is a fundamental, mysterious process that we don't fully understand. But Everett proposed a radically different solution. There's no collapse at all. Instead, every quantum measurement causes the universe to split. With every possibility encoded within the wave function, every quantum event, every single decision a particle could make. Actually, it does happen, but in a separate, branching universe. Let's illustrate this with a simple thought experiment. Consider an electron that has a 50% chance of spinning clockwise and a 50% chance of spinning counterclockwise. Before we measure its spin, it exists in a superposition of both states. According to the MWI, the moment we measure, the universe doesn't just choose one state. Instead, the universe splits into two. In one universe, the electron spins clockwise, and in the other, it spins counterclockwise. We, as observers, find ourselves in one of these branches experiencing only one outcome. Critically, the other universe, with its different outcome, continues to exist simultaneously. Now, this isn't just about electrons. It applies to every quantum event. The decay of a radioactive atom, the position of a photon, the seemingly random choice a particle makes when traversing a potential barrier. Each of these events triggers a split in the multiverse. The number of universes created with every quantum event is staggeringly vast, constantly multiplying as new quantum possibilities arise. The implications of the many worlds interpretation are profound. It suggests that an infinite number of parallel universes exist, each representing a different version of reality. In one universe, you might have chosen a different career path. Perhaps you met a different person, or maybe a slightly different historical event unfolded. These aren't just theoretical possibilities. According to MWI, they're actual, existing realities. One of the most challenging aspects of the MWI is that these other universes are, by definition, unobservable from our own. They exist alongside us, but are completely independent. We can never interact with them, nor can they interact with us. This isn't a comforting thought for some, but it's a logical consequence of the theory. There's no way to definitively prove or disprove the many worlds interpretation. It's a theory built on the foundations of quantum mechanics itself, a theory based on mathematical consistency, and the observed behavior of quantum systems. It offers a potentially elegant solution to the measurement problem, eliminating the need for a mysterious collapse. Furthermore, the MWI's sheer scale is captivating. It paints a picture of existence as something far grander and stranger than we typically imagine. While it might seem unsettling to contemplate an infinite number of you, living out slightly different lives in different universes, it represents a truly radical rethinking of our place within the cosmos. It reminds us that our universe, as we perceive it, is just one tiny facet of a much larger, far more complex and utterly mind-bending reality. The ongoing research into quantum mechanics continues to refine our understanding, and perhaps one day, we'll gain a deeper appreciation for the vastness and the strangeness of the multiverse. The hum of the lab was a quiet, persistent thrum, almost like a gentle heartbeat. Dr. Eris Thorne, a specialist in advanced computation, adjusted the delicate controls of the qubit array, a marvel of cooled superconductors, and intricately designed electromagnetic fields. This wasn't your typical computer. This was a machine built to exploit the strangest, most counterintuitive properties of the quantum world, and it was on the verge of demonstrating something truly revolutionary: quantum computing. The central idea driving this technology stems from a fundamental difference in how classical computers and quantum computers operate. Classical computers, the ones you use every day, store information as bits, tiny switches that can be either on-s representing a 1 or offs representing a 0. They perform calculations sequentially, one step at a time, like following a recipe carefully. Quantum computers, however, utilize qubits. A qubit isn't simply a 0 or a 1. Because of the phenomena we've discussed, superposition and entanglement, a qubit can exist as a combination of 0 and 1 simultaneously. It's like flipping a coin that's spinning in the air. It's neither heads nor tails until it lands. This inherent ability to exist in multiple states concurrently offers an exponentially larger computational space. With the Darjan's bits, a classical computer can represent one of two sup possibilities at any given time. But with Argendrich's qubits, a quantum computer can explore all two sup possibilities simultaneously. This creates the potential for solving problems that are completely intractable for even the most powerful supercomputers today. The key to harnessing this power lies in what's happening within the qubit array. Each qubit is carefully controlled by precisely tuned microwave pulses. These pulses, incredibly short bursts of energy, manipulate the quantum state of the qubit, guiding it towards a particular solution. The control algorithms are incredibly complex, relying on sophisticated mathematical models derived from quantum mechanics. Think of it like subtly steering a ship through turbulent waters. You don't force it to change direction abruptly, but rather apply a series of small, carefully timed adjustments. The challenge isn't just in creating these qubits, it's in maintaining their fragile quantum state. Qubits are extraordinarily sensitive to their environment. Even the tiniest vibrations, temperature fluctuations, or electromagnetic interference can cause them to decohere, to lose their quantum properties and collapse into a definite 0 or 1, just like the spinning coin finally landing. That's why the qubit array operates within a state of near absolute zero, colder than outer space, and is shielded from all external disturbances. Researchers are exploring various technologies to build qubits. Superconducting qubits, like those in the array, use circuits cooled to near absolute zero. Trapped ion qubits utilize individual ions, held in place by electromagnetic fields, and manipulated with lasers. Photonic qubits leverage the properties of individual photons, particles of light, to represent quantum information. Each approach has its own strengths and weaknesses, and the best technology is still actively being developed. The types of problems that quantum computers might eventually solve are staggering. drug discovery could be revolutionized, simulating molecular interactions to identify new drug candidates with unparalleled accuracy. Materials science could benefit from simulating the properties of novel materials before they are even synthesized. Financial modeling could become far more sophisticated, allowing for better risk management and investment strategies. Perhaps most profoundly, quantum computers could accelerate breakthroughs in artificial intelligence, enabling the development of truly intelligent machines. However, it's crucial to understand that quantum computers won't replace classical computers entirely. They're designed for very specific problems that involve exploring a vast number of possibilities concurrently. Everyday tasks like writing emails or browsing the internet will continue to be handled by classical computers. Instead, quantum computers will act as powerful co-processors, collaborating with classical computers to tackle the most complex and demanding challenges. The development of quantum computing is still in its early stages, a period often referred to as the noisy intermediate scale quantum, or NESQ era. Current quantum computers have a relatively small number of qubits, and these qubits are prone to errors. Researchers are working diligently to improve qubit coherence times, reduce error rates, and scale up the number of qubits. Dr. Thorne watched as the qubit array processed a complex simulation, a model of a protein folding process. The results, when visualized, revealed a surprisingly intricate and elegant solution, one that would have taken a classical supercomputer years to compute. It was a small step, perhaps, but a significant one in demonstrating the potential of this nascent technology. The future of computation was unfolding, not in the familiar realm of bits and bytes, but within the strange and wonderful world of quantum mechanics. The universe, as we perceive it, is constantly in motion. Stars blaze, planets orbit, and even the smallest dust motes dance in the sunlight. But what if the very space around us, the vast emptiness we call nothing, isn't truly nothing at all? Scientists have discovered that even in a vacuum, seemingly devoid of matter and energy, there exists a persistent, underlying energy, a concept they've termed zero-point energy. It's a profoundly strange idea, one that challenges our fundamental understanding of what empty space actually means. The discovery of zero-point energy stems from a clever experiment conducted in the 1920s by physicists Ronald Harrison and George Place. They focused a laser beam into a chamber filled with helium-4, a noble gas. Helium-4, like all matter, emits light when struck by photons. Harrison and Place expected the light to quickly scatter and diminish as it interacted with the walls of the chamber. However, they observed something unexpected. The scattered light persisted, not fading away as predicted by classical physics. Instead, it continued to bounce around within the chamber, albeit with a significantly reduced intensity. This seemingly anomalous behavior led them to propose a radical theory that the vacuum itself possessed an energy, a sort of background hum, that was constantly pushing back against the laser beam. They theorized that this energy wasn't coming from the helium atoms themselves, but from the quantum fluctuations inherent in the vacuum's structure. It's a concept deeply rooted in the principles of quantum mechanics, particularly the Heisenberg uncertainty principle. This principle dictates that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely we know one, the less we know the other. To illustrate, consider an electron. According to quantum mechanics, an electron within an atom isn't confined to a specific location. Instead, it exists as a fuzzy cloud of probability. This cloud represents the uncertainty in its position. Similarly, the uncertainty principle extends to energy. It states that we can't know the energy of a particle with perfect precision. There's always an inherent uncertainty. This uncertainty at the smallest scales translates into a constant fluctuation of energy in the vacuum. These quantum fluctuations aren't just random jitters. They're manifestations of the underlying quantum fields, the same fields that physicists explored in Part 6. These fields, like the electromagnetic field, are theorized to permeate all of space, even where no particles reside. When we apply the uncertainty principle to these fields, we get a continuous, albeit minuscule, creation and annihilation of virtual particles. These virtual particles appear for fleeting moments, borrowing energy from the vacuum before instantly returning it. They are incredibly short-lived, existing for only the tiniest fractions of a second, but their constant creation and annihilation generates an enormous amount of energy. This is the zero-point energy. The amount of energy involved is staggering. Calculations based on quantum field theory estimate that the zero-point energy density of the vacuum is approximately 10^117 joules per cubic meter. That's an unfathomably large number, more than 10 times the total energy output of the Sun. This immense energy represents a fundamental property of space itself, like the curvature of space-time. But instead of affecting movement, it's a constant source of potential energy. Scientists are actively exploring ways to harness this seemingly limitless energy source. Several theoretical approaches exist, ranging from Casimir effect devices to manipulating quantum vacuum fluctuations to generate power. The Casimir effect, first observed in 1995, provides a tangible demonstration of zero-point energy. When two uncharged, conductive plates are brought close together in a vacuum, they experience a measurable force, the Casimir force. This force arises because the vacuum fluctuations between the plates are differently constrained than outside, creating a pressure that pushes the plates together. While the concept of extracting usable energy from zero-point energy remains largely theoretical, the potential is immense. Imagine a world powered by the very fabric of space itself. However, realizing this vision presents significant challenges. The energy density is incredibly low, and the mechanisms for extracting and controlling quantum vacuum fluctuations are extremely complex. Moreover, questions remain about whether the very act of attempting to harness this energy could fundamentally alter it, potentially disrupting the delicate balance of quantum fluctuations. The continued investigation of zero-point energy is not just about finding a new source of power. It's fundamentally reshaping our understanding of the universe. It suggests that empty space is not a passive void, but an active, dynamic entity, teeming with potential and profoundly connected to the most fundamental laws of physics. It's a reminder that the most profound discoveries often come from challenging our most deeply held assumptions about what we believe to be nothing at all. It's a concept that invites us to contemplate the truly strange and wonderful nature of reality. The universe, as we experience it, the vastness of galaxies, the shimmering beauty of nebulae, the familiar blue of our sky is a breathtaking stage. But what if that stage isn't quite as solid or as still as we believe? What if, just a tiny fraction of a second, a fraction of a millimeter, beneath the surface of everything, reality itself is behaving in a way that defies our intuitive understanding? Scientists are increasingly exploring a concept called quantum foam, a radical idea suggesting that the very fabric of space-time isn't smooth and continuous, but instead, it's a chaotic, bubbling froth at the smallest scales. This isn't a matter of simple, artistic visualization. Quantum foam arises directly from the equations of quantum field theory, the most successful framework for understanding the fundamental forces of nature. These equations, particularly when applied to gravity, tell us that at incredibly small distances, the Planck length, a distance roughly 1.61035 meters, the classical rules of space and time simply break down. It's a place where the energy density is so extreme that the concepts of space and time, as we understand them, lose their meaning. The key ingredient in this bizarre picture is quantum uncertainty. Heisenberg's uncertainty principle states that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. This isn't a limitation of our measuring instruments, it's a fundamental property of the universe. At the Planck scale, this uncertainty becomes palpable. Virtual particles, fleeting combinations of energy and antimatter, constantly pop into existence and then annihilate each other. These aren't just theoretical constructs, they're a direct consequence of the energy fluctuations inherent in the quantum vacuum. Because of this constant, chaotic creation and annihilation, space itself isn't empty. Instead, it's filled with a seething, turbulent sea of these virtual particles and their corresponding energy fluctuations. The energy density is so high that it's thought to warp space-time itself, creating tiny, fluctuating wormholes and topological defects, minuscule tunnels and distortions in the geometry of the universe. These aren't stable, traversable wormholes like those in science fiction. They exist for only an unimaginably brief moment, lasting only the duration of the virtual particle's existence. Consider it like a boiling pot of water. The individual molecules don't maintain a perfectly still, predictable arrangement. They move, collide, and dissipate energy, creating ripples and turbulence. Similarly, the quantum vacuum isn't a serene void. It's a dynamic, bubbling chaos. The bubbles aren't physical bubbles in the traditional sense, but rather fluctuations in the energy field itself. These fluctuations generate minuscule gravitational fields, contributing to the overall curvature of space-time. The implications of quantum foam are profound. It suggests that gravity isn't just a force acting between objects with mass. It's an inherent property of the vacuum itself. The quantum foam is literally creating gravity. Furthermore, this fluctuating space-time might be responsible for phenomena we don't fully understand, such as dark energy, the mysterious force driving the accelerated expansion of the universe. If the vacuum is constantly fluctuating with energy, it's possible that some of these fluctuations contribute to the overall energy density of space, mimicking the effects of dark energy. Scientists are developing increasingly sophisticated theoretical models to explore the characteristics of quantum foam. One prominent model, the Swampland program, attempts to reconcile quantum field theory with general relativity by exploring the possible landscapes of space-time at the Planck scale. These models suggest that the geometry of space-time isn't a smooth manifold, as Einstein originally proposed, but rather a complex, branching structure influenced by quantum effects. Another intriguing idea arises from the concept of holographic duality. This theory proposes that our three-dimensional universe might be a projection from a two-dimensional surface, much like a hologram. Quantum foam could then be seen as the underlying structure of this two-dimensional surface, influencing the properties of our perceived 3D reality. It's crucial to understand that quantum foam is, at this point, largely theoretical. We don't have the technology to directly observe it. However, researchers are exploring indirect methods, such as analyzing the polarization of the cosmic microwave background radiation, the afterglow of the Big Bang, for subtle distortions caused by quantum fluctuations at the Planck scale. These analyses could provide crucial evidence to either confirm or refute the existence of this bizarre, bubbling reality. The very idea of quantum foam challenges our fundamental assumptions about the nature of space and time. It suggests a universe that is far more dynamic, complex, and fundamentally unpredictable than we ever imagined. It's a humbling reminder that our everyday experiences represent only a tiny, well-defined slice of a reality that is, at its most fundamental level, profoundly strange and utterly beautiful. The exploration of quantum foam isn't just about understanding the universe. It's about fundamentally redefining what we consider to be real. The quiet hum of the laboratory filled the space, not a harsh, mechanical sound, but a subtle vibration of focused observation. Dr. Ania Sharma meticulously adjusted the beam of a specialized spectrometer, its readings slowly resolving a puzzle that had captivated scientists for decades. How could something so unbelievably tiny, quantum mechanics, possibly explain the miraculous efficiency of life itself? For years, biology had operated on a scale of predictable, classical physics, charting the dance of molecules and reactions governed by established rules. But the evidence was mounting, suggesting a deeper, stranger truth. Quantum biology wasn't simply an intriguing theory, it was beginning to demonstrate demonstrable effects. The initial hints had come from studies of avian navigation. Birds, particularly young ones, seemed to possess an innate ability to find their way home from incredible distances, even under conditions where the magnetic field was weak and confusing. Scientists discovered that specialized cells in the bird's eyes contained proteins, notably cryptochromes, that exhibited incredibly sensitive responses to blue light. This light, at specific wavelengths, seemed to trigger a cascade of quantum events within these proteins. The photons, these tiny packets of energy, weren't just providing a visual signal, they were influencing the protein's structure and, consequently, its ability to detect the Earth's magnetic field. It was as though the birds were raiding the magnetic field at a quantum level, a process that depended on the quantum mechanical properties of these molecules. The field of photosynthesis, the process by which plants convert sunlight into energy, presented another compelling area of investigation. For decades, scientists understood the broad strokes chlorophyll molecules absorbed sunlight, initiating a series of electron transfers that ultimately created sugars. However, a growing body of research suggested that this process was far more intricate and, crucially, quantum in nature. Within chloroplasts, the organelles responsible for photosynthesis, researchers observed that excitation energy, the energy absorbed from sunlight, didn't simply flow directly from one chlorophyll molecule to the next. Instead, it appeared to explore multiple pathways simultaneously, exploiting the phenomenon of quantum superposition. Superposition, a core concept in quantum mechanics, allows a particle, in this case, an excitation to exist in multiple states at once. It's like a coin spinning in the air. It's neither heads nor tails until it lands. In photosynthesis, this meant that the excitation energy wasn't confined to a single route. It seemingly tried all possible pathways for transferring energy to the next molecule. The trick, however, wasn't simply chaotic exploration. Quantum coherence, the ability of these superimposed states to remain correlated, allowed the system to rapidly narrow down its search, quickly identifying the most efficient route to energy transfer. This coherent process dramatically increased the efficiency of photosynthesis, minimizing energy loss and maximizing the conversion of sunlight into usable energy. The investigation extended beyond simple energy transfer. Enzymes, the biological catalysts that speed up chemical reactions within cells, were also shown to be susceptible to quantum effects. Enzymes are complex molecules with active sites designed to bind to specific substrates and facilitate reactions. Recent research indicated that the precise orientation of molecules within these active sites, critical for efficient catalysis, could be influenced by quantum tunneling. Quantum tunneling is another peculiar quantum phenomenon where a particle can pass through a barrier, even if it doesn't have enough energy to overcome it classically. In enzyme catalysis, this meant that the substrate molecules could tunnel through the energy barriers surrounding the active site, dramatically accelerating the reaction rate. Furthermore, the vibrational modes of molecules within enzymes Tiny movements that play a crucial role in their function were found to exhibit quantum coherence. These coherent vibrations help to stabilize the enzyme's structure and optimize the interaction between the enzyme and its substrate. The implications were staggering. The delicate dance of life, at its most fundamental level, was governed by the probabilistic, interconnected nature of the quantum world. Scientists were beginning to develop sophisticated computer models to simulate these quantum biological processes, attempting to understand how the intricate interplay of superposition, coherence, and tunneling contributed to the astonishing efficiency and adaptability of living organisms. These models weren't just theoretical exercises, they were generating testable predictions. Researchers were designing experiments to directly observe quantum coherence in biological systems, using techniques like fluorescence microscopy and electron paramagnetic resonance. The field was still young, filled with questions and challenges. Understanding how quantum effects are maintained and shielded from the noise of the classical world, the thermal vibrations and interactions that could disrupt quantum coherence, remained a key hurdle. However, the progress was undeniable. Quantum biology was transforming our understanding of life itself, revealing a hidden layer of complexity and elegance, one that demonstrated that the universe, even within the confines of a single cell, was fundamentally quantum. It was a reminder that the familiar world we perceive isn't the whole story. There are realms of reality, governed by principles so strange and counterintuitive that they redefine our very notion of what is possible. The universe, as we experience it, is often a world of stark contrasts: hot and cold, light and dark, solid and liquid. But peering into the realm of quantum physics reveals a far stranger reality, one where particles can exist in multiple states simultaneously, like a coin spinning endlessly in the air, both heads and tails until it lands. This is the phenomenon of superposition, and it's a cornerstone of quantum mechanics. However, this incredible state, this ability for a particle to be in two places, or two energy levels, at the same time, is remarkably fragile. It doesn't last forever. The universe, it seems, has a vested interest in settling things down, and the process by which it does so is known as decoherence. Decoherence isn't a dramatic event, a sudden collapse of the quantum world. Instead, it's a gradual, almost insidious process. It's the dance between a quantum system, a single electron, a photon of light, or even a small molecule, and its environment. Think of it like trying to balance a perfectly still tower of blocks. The slightest disturbance, a breeze, a vibration, even a stray thought, can knock it over. Similarly, any interaction with the environment introduces information that fundamentally changes the quantum system. At the heart of decoherence is the concept of degrees of freedom. A degree of freedom refers to any way a system can change. For an electron, these could include its position, its momentum, or its spin, a fundamental property that's often described as intrinsic angular momentum. When a particle is in superposition, all possible states corresponding to these degrees of freedom are present simultaneously. But the environment, everything around the particle, is constantly buzzing with energy, vibrating with countless particles, and carrying information. These environmental interactions, even if incredibly weak, act like tiny probes, constantly measuring the particle's properties. When a photon, for example, interacts with air molecules, it's affected by their vibrational modes. The act of measuring, or even simply being influenced by, changes the superposition. The particle knows it's being observed, and that knowledge forces it to choose a single state. It's as if the environment is whispering, "Okay, you can be in this state now." The crucial element is that these interactions don't just change the probability of finding the particle in a specific state. They fundamentally alter the state itself. Consider a very sensitive instrument designed to measure the spin of an electron. As the electron interacts with the instrument's components, the metal, the wires, even the surrounding air, the instrument subtly biases the electron towards a particular spin direction. This isn't a conscious observation by a human. It's simply the unavoidable consequence of the electron's interaction with the instrument's energy. Mathematical models, developed primarily by Nicholas Gisin and collaborators, have become essential in understanding decoherence. These models utilize concepts from quantum information theory to describe how information about the particle's quantum state leaks into the environment. The rate at which this leakage occurs is quantified by a parameter called the dephasing time. This time represents the duration for which a quantum system can maintain its superposition before it becomes effectively classical. The dephasing time is incredibly short, typically measured in attoseconds, a billionth of a second, or even shorter. That's why we don't see macroscopic objects in superposition. The sheer number of environmental interactions they experience would instantly collapse any potential quantum state. The denser the environment, the faster the decoherence occurs. A single, isolated atom in a vacuum will maintain its superposition for far longer than a particle trapped within a complex molecule or exposed to the vibrations of a noisy room. Interestingly, decoherence isn't simply a destructive process. While it eliminates superposition, it also creates classical correlations. The interaction between the quantum system and the environment establishes a definite relationship between their properties. For example, if you measure the spin of an electron that was initially in a superposition, the subsequent measurements will consistently show a specific spin orientation, a correlation arising from the initial interaction. Scientists are actively exploring ways to manipulate decoherence, both to understand it better and to potentially harness its effects. For example, researchers are investigating the use of carefully designed quantum memories, systems designed to protect quantum information from environmental noise. These memories, often based on trapped ions or superconducting circuits, aim to extend the dephasing time, allowing for more complex quantum computations. The study of decoherence is fundamentally changing our understanding of the boundary between the quantum and classical worlds. It highlights the intimate connection between observation and reality, and reveals that the classical world we experience is not a fundamental one, but rather a highly evolved and remarkably stable state that has emerged through the process of decoherence. It's a reminder that even the smallest interactions can have profound consequences in the bizarre and beautiful realm of quantum mechanics. The universe, as we experience it, is a stunning symphony of forces. We see gravity pulling us towards the Earth, electromagnetism holding atoms together, and the strong and weak nuclear forces governing the heart of the atom. Yet, for a very long time, these beautiful, well-understood laws of physics existed in separate, almost walled-off gardens. General relativity, Einstein's masterpiece, beautifully described gravity as a curvature of space. Time, the very fabric of the cosmos, caused by mass and energy. It explained the orbits of planets, the bending of light around massive objects, and the expansion of the universe itself. Quantum mechanics, on the other hand, explained the bizarre, counterintuitive behavior of matter and energy at the smallest scales. It told us about the quantization of energy, the uncertainty principle, and the strange phenomenon of superposition, where a particle can exist in multiple states simultaneously until observed. The problem arose when physicists tried to apply both theories to the most extreme environments imaginable, black holes, and the very beginning of the universe, moments after the Big Bang. At these scales, gravity becomes unbelievably strong, and quantum effects, the uncertainty and probabilistic nature of the quantum world, become overwhelmingly dominant. General relativity, with its smooth, continuous description of space, time, simply breaks down. It predicts singularities, points of infinite density, where our current laws of physics cease to exist. Similarly, quantum mechanics struggles to account for the large-scale structure of the cosmos. This incompatibility has driven decades of theoretical exploration, a quest to find a single, overarching theory that can seamlessly integrate these two pillars of modern physics. Several promising approaches have emerged, each attempting to redefine our understanding of space, time, and the fundamental nature of reality. One of the leading contenders is string theory. Instead of viewing elementary particles as point-like objects, string theory proposes that they are, in fact, incredibly tiny, vibrating strings. These strings, existing in 10 or 11 dimensions, we only perceive 3 spatial and 1 temporal, vibrate at different frequencies, giving rise to the diverse range of particles we observe. The theory elegantly avoids the singularities predicted by general relativity, as the strings themselves are never truly compressed to a point. However, string theory isn't without its challenges. The extra dimensions are thought to be curled up at incredibly small scales, far beyond our current ability to directly observe them. Furthermore, string theory is incredibly complex mathematically, and making testable predictions has proven exceptionally difficult. Another approach is loop quantum gravity, LQG. This theory takes a radically different tack, suggesting that space, time itself is not a continuous, smooth fabric, but rather is composed of discrete loops or quanta of space. These loops are constantly interacting and forming a quantum network. LQG predicts that space, time is grainy at the Planck scale, implying that space, time is fundamentally quantized, much like energy is quantized in quantum mechanics. The mathematical framework of LQG is complex, but it offers a potential resolution to the singularity problem by introducing a minimum length scale, the Planck length, effectively preventing the collapse of matter into a point. A particularly intriguing consequence of LQG is the possibility of a multiverse, a vast collection of universes, each with potentially different physical laws and constants. This arises from the theory's inherent uncertainty and the multiple possible configurations of the quantum network. Another significant area of investigation is asymptotic safety gravity. This approach attempts to reconcile general relativity with quantum mechanics without invoking new fundamental objects like strings. Instead, it proposes that gravity itself becomes safe at high energies, meaning that the strength of the gravitational force doesn't increase infinitely as it approaches the Planck scale. This requires modifying the behavior of the gravitational field at these extreme energies, effectively smoothing out the singularities and offering a consistent framework for quantum gravity. The search for a theory of quantum gravity is not merely an academic exercise. It's driven by the potential to unlock the secrets of the Big Bang and the nature of black holes. Understanding these extreme environments is crucial to refining our cosmological models and potentially even finding ways to manipulate space, time itself. Current research involves sophisticated simulations, advanced mathematical techniques, and exploring the limits of our experimental capabilities. While a complete and universally accepted theory of quantum gravity remains elusive, the ongoing investigation is reshaping our fundamental understanding of the universe. It's a testament to the human desire to explore the unknown, to grapple with the most profound questions about existence, and to unravel the deepest mysteries of space, time, and the very fabric of reality. The pursuit of this elusive theory pushes the boundaries of our knowledge and reminds us that the universe may hold even more astonishing secrets than we can currently imagine. The year is 1926. Vienna, Austria. A city brimming with intellectual energy, but also shadowed by the anxieties of the time. physicist Erwin Schrödinger, a brilliant mind grappling with the increasingly bizarre implications of quantum mechanics, found himself wrestling with a particularly persistent and unsettling puzzle. He hadn't set out to create a nightmare, but rather a tool to illustrate the core strangeness of the theory. And this tool became known as the Schrödinger's cat thought experiment. Schrödinger, a deeply thoughtful man, was uncomfortable with the implications of the Copenhagen interpretation, the prevailing understanding at the time, which suggested that a quantum system exists in a superposition of states until measured. This meant something like an electron could be in two places at once, or spinning both clockwise and counterclockwise simultaneously, until an observation forced it to choose one state. The problem wasn't just that this seemed counterintuitive, it was that it applied, seemingly, to everything. Schrödinger's cat wasn't designed to be a reflection of reality, but a dramatic illustration of the mathematics. He conceived of a sealed steel box. Inside this box resided a small, beautiful, and undeniably live cat. Alongside the cat was a radioactive atom, a device capable of decaying, emitting radiation with a 50% probability of happening within a given time period. Now, this wasn't just any radioactive atom. It was connected to a complex apparatus. If the atom decayed, it triggered a mechanism that released a tiny hammer. This hammer, in turn, smashed a vial of poisonous gas. If the vial broke, the gas filled the box, and the cat would die. However, and this is the crucial element, until someone opened the box and observed the system, quantum mechanics dictates that the atom exists in a superposition. It's neither decayed nor not decayed. It's both simultaneously. Schrödinger's genius lay in extending this idea to the macroscopic world. Because the atom is in a superposition, the hammer isn't smashed, and the vial remains intact. Consequently, the cat remains both alive and dead simultaneously. It's a profoundly unsettling image, isn't it? We instinctively understand that a cat can only be one or the other alive or dead. Our everyday experiences are built on the assumption of definite states. A chair is either there or it isn't. A light is either on or off. Schrödinger's cat challenges this fundamental intuition. The experiment doesn't claim to describe a real situation, but rather to highlight the consequence of applying quantum rules to objects of significant size. The mathematical framework, derived from the Schrödinger equation, a fundamental equation describing the evolution of quantum systems, allows for the calculation of the probabilities associated with the cat's state. According to the equation, until the box is opened and the system is observed, the cat exists in a probabilistic blend of alive and dead states, each with a 50% chance of occurring. The act of observation, the opening of the box, and the measurement of the system forces the wave function, the mathematical description of the quantum state, to collapse, resolving the superposition and determining the cat's fate. Now, it's important to understand that Schrödinger wasn't suggesting that there was actually a cat in a box. He created this thought experiment to provoke discussion and expose the profound strangeness of the theory. He was questioning whether quantum mechanics, as interpreted at the time, could truly be applied to the macroscopic world without leading to logical contradictions. It was a deliberate attempt to critique the Copenhagen interpretation, not to endorse a specific view. The implications of the thought experiment extend far beyond the fate of a single cat. It forces us to confront the role of the observer in quantum mechanics. Does observation fundamentally alter reality? Does the act of measuring a quantum system change its state? The question remains a subject of ongoing debate and research among physicists. Some interpretations, like the many worlds interpretation, attempt to avoid the collapse of the wave function by proposing that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome. Schrödinger's cat has become a cornerstone of discussions about the foundations of quantum mechanics. It's been endlessly analyzed, debated, and used as a springboard for exploring various interpretations of quantum theory. While the image of a cat trapped in a box is unsettling, it serves as a potent reminder of the counterintuitive nature of the quantum world, a world where reality, as we understand it, may not be so solid after all. The experiment continues to stimulate scientific inquiry and philosophical reflection, and it's a reminder that some of the most fundamental questions about the universe remain unanswered. The universe, as we generally understand it, seems to operate on a principle of cause and effect. A billiard ball hits another, and it moves. A push makes a child fall. These are simple, predictable relationships. But what if this fundamental assumption, this notion of localized influence, could be fundamentally wrong, especially when we're dealing with the smallest building blocks of reality? This is precisely the question that Albert Einstein, along with Boris Podolsky and Nathan Rosen, wrestled with in the early 1930s, leading to what became known as the EPR paradox. Their concern wasn't about the strangeness of quantum mechanics itself, but rather about whether it could be complete. They believed that quantum mechanics, with its description of particles existing in multiple states simultaneously, was incomplete, and that there must be hidden variables, properties that we simply haven't discovered yet, governing these behaviors. These hidden variables, they argued, would explain the seemingly random outcomes observed in experiments like those involving photon polarization. The key to understanding the challenge came with the work of John Stuart Bell. Bell wasn't trying to disprove quantum mechanics, but rather to formulate a mathematical test to determine if local realism was correct. Local realism, in its simplest form, consists of two core assumptions. First, that an object's properties are determined at a specific point in space and time, and second, that no influence can travel faster than the speed of light. In other words, if you measure the polarization of one photon, that measurement shouldn't instantaneously affect the polarization of a distant, entangled photon, regardless of the distance separating them. Bell devised a set of inequalities, now famously known as Bell's inequalities, which would hold true if local realism were correct. These inequalities provided a mathematical limit on the statistical correlations that could be observed between measurements performed on two entangled particles. The beauty of Bell's approach was that it offered a way to experimentally test these assumptions directly. He developed a set of correlations that could be calculated based on the assumptions of local realism, and compared them to the correlations actually observed in experiments. The crucial component was entanglement, a phenomenon where two or more particles become linked in such a way that they share the same fate, no matter how far apart they are. Imagine creating a pair of entangled photons. We could set up a device that measures the polarization of one photon along a specific axis. The moment we make that measurement, the polarization of the other photon instantly becomes correlated with our measurement, even if it's light years away. The experiments, beginning with those spearheaded by Alain Aspect and his team in the late 1970s, were meticulously designed to test Bell's inequalities. Aspect's team used rotating detectors, cleverly arranged to scramble the directions along which the photons were measured. This ensured that the photons weren't influenced by any predetermined, hidden direction. The goal wasn't to try to communicate with the other photon, but simply to measure their correlations. The results were astonishing. Repeatedly, and with increasing precision, the experimental measurements consistently violated Bell's inequalities. This meant that the correlations observed between the entangled photons were stronger than what could be predicted if local realism were true. It wasn't that the photons were, trying to violate the inequalities. The violation was inherent in the quantum mechanical description itself. The act of measuring one photon instantaneously influenced the state of the other, regardless of the distance. This is where the concept of non-locality takes center stage. Non-locality doesn't imply that information is being sent faster than light that would violate Einstein's theory of relativity. Instead, it suggests a deeper connection between the particles, a fundamental interconnectedness that transcends our everyday understanding of space and time. The implications are profound. It means that reality at the quantum level isn't entirely determined by local, spatially confined properties. Instead, the entangled particles exist in a shared, holistic state, even when separated by vast distances. To illustrate, consider a coin flipped simultaneously in two different locations. Before either person looks, it's neither heads nor tails. It exists in a superposition of both states. When one person looks and sees heads, the other instantly knows their coin is tails, even without looking. While this analogy isn't perfect, it captures the essence of the instantaneous correlation. The experimental evidence overwhelmingly supports the violation of Bell's inequalities, cementing the reality of quantum non-locality. While Einstein remained skeptical, clinging to the idea of spooky action at a distance, the overwhelming experimental data has forced a reassessment of our intuitive notions about the universe. It's a reminder that the quantum world operates according to rules that are profoundly different from those governing our everyday experience. These seemingly bizarre connections demonstrate that the universe isn't simply a collection of separate objects interacting locally. It's a deeply interconnected web of quantum relationships, a reality that continues to challenge and fascinate scientists and philosophers alike. The continued exploration of quantum entanglement promises to unlock further secrets about the very fabric of space-time and the nature of existence itself. The universe, it turns out, doesn't always behave like things we're used to seeing. It's not simply a collection of objects neatly orbiting each other, or particles moving in straight lines. At the very smallest scales, the rules are different. And one of the most peculiar of these differences concerns something called spin. It's a property inherent to elementary particles, electrons, quarks, even photons, and it's utterly baffling from a classical perspective. We're used to thinking of an object's rotation, like a spinning top. It has a defined axis of rotation, and it's clearly generating angular momentum. But quantum spin isn't like that. It's not a particle physically rotating around an axis. Instead, it's as if the particle itself possesses an intrinsic moment of angular momentum, a kind of built-in inherent spin. It's a completely abstract property, existing solely within the particle itself. The concept arose from early 20th century experiments, particularly those involving the spectra of emitted light from excited atoms. Scientists observed that atoms emitted light at very specific wavelengths, distinct lines in the spectrum. Initially, physicists struggled to explain why these transitions occurred at exactly these frequencies. Max Planck's idea of energy quantized, that energy comes in discrete packets, provided a starting point. But it still didn't fully account for the observed patterns. Then, in 1921, Satyendranath Bose, building on work by blackbody radiation theory, developed what's known as the Bose-Einstein statistics. This theory explained the spectral lines by proposing that photons, the particles of light, behaved not as continuous waves, but as discrete packets of energy quanta, each carrying a specific amount of angular momentum. The crucial breakthrough came when physicists realized that these quanta of light, or photons, possessed a definite, intrinsic angular momentum. This angular momentum wasn't derived from the photon's movement through space, it was simply there, a fundamental characteristic of the particle. And this wasn't limited to photons. Soon it was recognized that electrons, too, exhibited this intrinsic angular momentum. The simplest model described spin as if the electron were somehow constantly spinning, generating a magnetic field. However, this is a somewhat misleading analogy. The electron doesn't actually spin in the classical sense. Instead, the spin is described mathematically using quantum operators. These operators represent the fundamental properties of the spin. One of the most important results came from a 1932 paper by Paul Dirac, who successfully unified quantum mechanics with special relativity. Dirac's relativistic formulation of quantum mechanics predicted that spin angular momentum is as quantized, meaning it can only take on specific, discrete values. For electrons, the only allowed values are multiples of 1/2, represented as S1/2, 3/2, 5/2, and so on. These S values determine the amount of angular momentum the particle possesses. This quantization has profound implications. Because spin is quantized, it creates a magnetic dipole moment for the particle. This means that the particle behaves like a tiny bar magnet, with its magnetic field aligned with its spin. This is why electrons in atoms interact with magnetic fields. They're essentially tiny magnets responding to external forces. Furthermore, spin plays a vital role in the stability of atoms. Without spin, the electrons would quickly spiral into the nucleus, and atoms wouldn't exist as we know them. The implications extend far beyond simply explaining atomic spectra. Spin is fundamental to many technologies. Magnetic resonance imaging, (MRI), for example, relies directly on the interaction between nuclear spin, a property linked to atomic spin, and magnetic fields. Similarly, the operation of hard drives, which store data by magnetizing tiny regions on a rotating platter, relies on the principles of spin. Scientists are now exploring the possibility of manipulating spin for use in quantum computing. Quantum computers aim to harness the strange properties of quantum mechanics, including superposition and entanglement, to perform calculations far beyond the capabilities of traditional computers. Spin states, the up or down states of an electron spin, are being investigated as potential bits of information within these quantum computers. Furthermore, the study of spin is pushing the boundaries of our understanding of the universe. Experiments are attempting to test fundamental symmetries of nature, symmetries that might be broken by the interaction of spin with gravity, a long-sought connection that could revolutionize our understanding of the cosmos. Despite the intricate math involved, the concept of spin boils down to a surprisingly simple idea that some elementary particles possess an intrinsic angular momentum, a fundamental property that governs their behavior and interacts with the forces of nature in extraordinary ways. It's a reminder that the universe, at its smallest scales, operates according to rules that are profoundly different from our everyday experience, and a testament to the enduring power of scientific inquiry to unravel the deepest mysteries of existence. The universe, as we understand it, isn't built of simple, independent bricks. It's constructed from something far more intricate, something that behaves in ways that challenge our everyday intuitions about how the world should work. The standard model of particle physics, our best current description of the fundamental building blocks and forces, has a crucial piece missing: a complete explanation of the strong force. That's where quantum chromodynamics, or QCD, comes in. QCD is the theory that governs the behavior of the most fundamental particles that make up protons, neutrons, and, indeed, nearly all the matter we see around us. At its core, QCD describes the interactions between quarks and gluons. Quarks are the smallest known constituents of matter, and they come in 6 different flavors: up, down, strange, charm, bottom, and top. Each flavor has a different mass, though the up and down quarks are the most common, forming the building blocks of everyday matter. Gluons, on the other hand, are the force carriers of the strong force, tiny. electrically neutral particles that mediate the interactions between quarks. Think of them not as little bullets, but as messengers, constantly zipping around, exchanging information and holding the quarks together. The key difference between QCD and the electromagnetic force, which governs interactions between charged particles like electrons and protons, lies in the nature of the force itself. The electromagnetic force is long-range. The farther apart charged particles are, the weaker the force. But the strong force is something entirely different. It's short-rangey. This means that quarks are only bound together within composite particles like protons and neutrons. As soon as quarks get too far apart, the strong force rapidly weakens. It's a profoundly confining force. This short-range nature of the strong force arises from a peculiar property called a color charge. Unlike electric charge, which comes in positive and negative, color charge isn't a property we perceive directly. Instead, quarks carry three color charges: red, green, and blue. These aren't literal colors, of course. They're just labels physicists use to describe this fundamental aspect of the particles' interaction. The force between quarks is determined by these color charges, like magnets with north and south poles. Red quarks attract red quarks. Red quarks attract green quarks, and so on. This creates a complex web of interactions. Now, here's where it gets even more interesting. Gluons themselves also carry color charge. They aren't just mediating the interaction between quarks, they are part of the interaction itself. A gluon carries a combination of color and anti-color charge, for example, red and anti-green. This self-interaction of gluons is a major reason why QCD is so incredibly complex to calculate. It's not simply a matter of adding up the forces between quarks. The gluon's own color charge creates a constantly fluctuating and incredibly dynamic environment. The mathematical description of QCD is based on a quantum field theory. This means that each quark and gluon isn't just a single particle, but rather a localized excitation of a quantum field that permeates all of space. These fields constantly fluctuate, creating a sea of virtual particles, short-lived quarks and gluons that pop into existence and then disappear again, governed by the laws of quantum mechanics. It's within this sea of virtual particles that the strong force interactions take place. Calculating the forces within QCD is extraordinarily difficult. The self-interaction of gluons leads to a phenomenon called confinement. This means that you can't isolate a single quark. If you try to pull a quark out of a proton, the energy you put in creates new quark-antiquark pairs from the vacuum, effectively forming new hadrons, composite particles made of quarks and gluons. It's like trying to pull a single thread from a woven fabric. The fabric itself changes to hold itself together. The behavior of quarks and gluons at extremely high energies, the conditions that existed in the very early universe, is described by perturbative QCD. This approach uses approximations to calculate the forces at energies significantly higher than those involved in the interactions between ordinary hadrons. However, at lower energies, the interactions become so complex that perturbative QCD breaks down, and we need to rely on more sophisticated techniques, such as lattice QCD, a computational method that discretizes space and simulates the interactions between quarks on a computer. Lattice QCD provides a way to calculate hadron properties, things like masses and decay rates, with unprecedented accuracy. It's a computationally intensive process, requiring supercomputers to simulate the quantum interactions of quarks and gluons. Despite the challenges, lattice QCD has been instrumental in refining our understanding of the strong force and the properties of hadrons. The study of QCD isn't just an academic exercise. It's crucial for understanding the stability of matter, the formation of heavy elements in stars, and the evolution of the universe. It also has implications for technologies like particle accelerators, which rely on a deep understanding of the strong force to manipulate and study fundamental particles. As we continue to probe the mysteries of the universe, QCD will undoubtedly remain a cornerstone of our understanding of matter and the forces that shape it. The universe, at its most fundamental level, seems to harbor a secret, a profound awareness of itself. It's not a conscious, thinking entity in the way we understand it, but rather the very act of looking, of attempting to measure a quantum system, fundamentally alters its behavior. This isn't a matter of clumsy instruments, disturbing, delicate experiments. It's woven into the very fabric of reality, a consequence of how these tiny particles exist before we try to pin them down. Consider an electron. Before we attempt to determine its position, it doesn't possess a single, definite location. Instead, it exists in a state described as a superposition, a bizarre combination of all possible positions within a given space. It's like a blurry cloud of probabilities, a multitude of possibilities coexisting simultaneously. The electron isn't not at a specific spot. It simply doesn't have a single, defined location until we force it to choose. This isn't a question of our ignorance. It's the fundamental state of the particle itself. Now, let's introduce the measurement. Measurement, in quantum mechanics, isn't merely the recording of a value. It's an interaction, a deliberate attempt to gain information about the system. It's the act of shining light on an electron, sending a wave of energy towards it, or perhaps interacting it with another particle. This interaction causes the superposition to collapse. Suddenly, the blurry cloud of probabilities resolves into one definite location. The electron picks one possibility from the many, and that's the outcome we observe. The exact mechanism of this collapse remains one of the most debated and mysterious aspects of quantum mechanics. Physicists have proposed various interpretations, each attempting to explain how and why this happens. One prominent idea, known as the Copenhagen interpretation, suggests that the wave function, the mathematical description of the superposition, simply vanishes upon measurement. It's as if the act of observing removes the possibility of multiple outcomes. However, this interpretation raises further questions. What constitutes a measurement? Does it require a conscious observer? Some interpretations explore the idea that any interaction with the environment, no matter how small, can trigger this collapse. A photon bumping into a molecule, for example, could be enough to force an electron to choose a specific position. Another fascinating concept is the role of the apparatus used in the measurement. The famous double-slit experiment demonstrates this beautifully. When electrons are fired at a barrier with two slits, they create an interference pattern, a pattern characteristic of waves. This suggests that each electron is passing through both slits simultaneously, interfering with itself like a wave. But when we attempt to observe which slit the electron passes through, by placing a detector at one of the slits, the interference pattern disappears, and the electrons behave like particles, passing through one slit or the other. The very act of observing forces the electron to make a definite choice. The observer isn't necessarily a human being. The observer, in this context, refers to any interaction that causes the wave function to collapse. It's this interaction that fundamentally alters the state of the quantum system. This has led to profound philosophical debates about the nature of reality and the role of consciousness. It's crucial to understand that this isn't about us personally observing the universe. It's about the inherent disturbance caused by any interaction. Even the most sophisticated measuring instruments introduce a degree of disturbance. The goal isn't to eliminate this disturbance, but to understand and account for its effects. The mathematics of quantum mechanics, particularly the Schrödinger equation, provides a framework for predicting how these superpositions evolve over time. but it doesn't fully explain why they collapse. The collapse is a sudden, discontinuous event, a stark contrast to the smooth, predictable behavior we see in the macroscopic world. Consider a quantum computer. These machines utilize qubits, which, unlike classical bits that represent 0 or 1, can exist in a superposition of both states simultaneously. This allows quantum computers to perform certain calculations far more efficiently than classical computers. However, maintaining this superposition is incredibly challenging, as any interaction with the environment can cause the qubits to decohere, to lose their superposition, and collapse into a definite state. The fragility of superposition highlights the profound impact of observation in the quantum realm. The ongoing research into quantum mechanics continues to push the boundaries of our understanding. Scientists are exploring new ways to manipulate superpositions and to harness their potential for technological advancements. While the mysteries of quantum collapse remain, one thing is certain. The universe at its smallest scales operates under rules far stranger and far more interconnected than we ever imagined. It's a reminder that the very act of seeking knowledge can fundamentally shape the thing we seek to understand. The universe, as we've come to understand it through the lens of quantum mechanics, isn't simply a giant, clockwork machine ticking along with predictable regularity. Instead, it operates on principles that, frankly, seem to defy our everyday intuition. While the spin of particles and the force binding quarks together reveal a hidden complexity, perhaps the most radical concept emerging from this field is the possibility of fundamentally different ways of encoding and processing information. This is where quantum information theory enters the picture, offering a pathway to computing and communication that could reshape our world in ways we are only beginning to grasp. At the heart of quantum information lies the idea of the qubit. The traditional computer, the one you're using to read this, stores information as bits. A bit can only be in one of two states, a 0 or a 1. It's like a light switch, either on or off. This binary system, while incredibly useful for representing and manipulating vast quantities of data, is inherently limited. It's a system built on absolute states. Quantum mechanics, however, thrives on uncertainty and superposition. A qubit, short for quantum bit, leverages this. Instead of being strictly a 0 or a 1, a qubit can exist in a state that is both 0 and 1 simultaneously. It's not that the qubit is flickering rapidly between the two states. It's existing in a probabilistic combination of both until measured. This both-at-once state is called superposition. Think of it like a coin spinning in the air. Before it lands, it's neither heads nor tails. It's in a blurred state that encompasses both possibilities. The exact proportions of each state, the likelihood of it being a 0 or a 1, are defined by probabilities. The key to understanding this relies on a mathematical concept called the Bloch sphere. It's a 3D representation of a qubit state. Instead of a simple on-off switch, a qubit is represented as a point on the surface of this sphere. The position of that point determines the probability of the qubit collapsing into either the 0 or 1 state when measured. Different points on the sphere represent different superpositions, each with its own unique set of probabilities. Now, what makes this so powerful for information processing? Because a qubit can represent multiple values simultaneously. A quantum computer built with qubits has the potential to perform calculations in a dramatically different way than a classical computer. Imagine trying to find the correct path through a maze. A classical computer would try each path one at a time, systematically eliminating dead ends. A quantum computer, thanks to superposition, could explore all paths simultaneously. This parallel processing capability could revolutionize fields like drug discovery, materials science, and cryptography. Another crucial aspect is entanglement. This phenomenon, intimately linked to qubits, takes the parallel processing capabilities of a quantum computer to an entirely new level. When two or more qubits become entangled, their fates are intertwined, regardless of the distance separating them. Measuring the state of one entangled qubit instantly determines the state of the other, even if they are light years apart. It's like having two of those spinning coins magically linked. If one lands heads, the other instantly lands tails. While entanglement doesn't directly allow for faster than light communication, a common misconception, it does provide a way to correlate quantum computations across multiple processors. This is vital for creating truly massive quantum computers. Furthermore, manipulating entangled qubits allows for certain algorithms, like Shor's algorithm for factoring large numbers, to achieve exponential speedups compared to their classical counterparts. This is why quantum computers pose a significant threat to modern encryption methods, which rely on the difficulty of factoring large numbers. The practical construction of qubits is extraordinarily challenging. Maintaining superposition and entanglement requires incredibly precise control and isolation from the environment. Any interaction with the outside world, even a tiny vibration or a stray photon, can cause the qubits to decohere, meaning they lose their quantum properties and collapse into a definite 0 or 1 state. Scientists are exploring various physical systems to create stable qubits, including trapped ions, superconducting circuits, and topological qubits, each with its own advantages and disadvantages. Despite the hurdles, the potential rewards are enormous. Quantum cryptography, utilizing the principles of quantum mechanics to securely transmit information, is already being developed. Quantum sensors, leveraging the sensitivity of qubits to changes in their environment, promise unprecedented accuracy in measuring things like gravitational fields and magnetic fields. The ongoing research into quantum algorithms continues to reveal new possibilities for solving problems currently intractable for even the most powerful supercomputers. The journey into quantum information theory is a journey into the heart of the universe's strangest and most fascinating secrets. It's a realm where the rules of classical physics no longer apply, and where the very nature of reality is fundamentally different from what we experience every day. As our understanding of these principles deepens, we unlock not just new technologies, but a deeper appreciation for the interconnectedness and underlying complexity of everything around us. The universe, as we typically understand it, is built on a fundamental principle: entropy. It's the tendency for things to become more disordered over time. A perfectly stacked tower of blocks will inevitably topple. A glass dropped from a table will shatter. Heat flows from hot to cold. This increase in disorder, this relentless march towards randomness, is what physicists call entropy, and it defines the arrow of time, the direction in which time appears to flow. We experience this constantly. We remember the past, but we can't remember the future. The universe seems to be moving from order to disorder, and our perceptions align with this established framework. But what if that framework wasn't quite so absolute? What if there existed a state of matter, a crystalline structure, that actively resisted this inherent disorder, appearing to maintain order without any external energy input? The discovery of time crystals represents just such a challenge to our deeply ingrained understanding of time. It began with a theoretical prediction, initially proposed by physicist Lev Lebedev in 2012. Lebedev suggested that certain carefully designed, frustrated crystals, meaning structures with repeating patterns that are constrained from easily shifting, could spontaneously develop a rhythmic, repeating pattern of their own. The crucial element wasn't just the repeating arrangement, but the way that pattern persisted. Unlike a vibrating crystal, which gradually loses energy and slows down, a time crystal's pattern remains stable over an indefinitely long period, effectively keeping time, without needing a continuous external source of energy. The confirmation of these theoretical predictions came in 2016, and it was a truly remarkable moment. Researchers at the California Institute of Technology, led by David Oshalom, created a system using ytterbium ions, individual atoms with tightly controlled energy levels trapped in a magnetic field. They meticulously manipulated the energy of these ions, creating a complex, three-dimensional lattice. The surprising result was the emergence of a perfectly regular, oscillating pattern of spins, like the hands of a clock, without any external driving force. The oscillation wasn't caused by vibrations. It was a fundamental property of the crystal itself, a stable, self-sustaining rhythm. What makes this so mind-bending is the apparent defiance of the arrow of time. Classical physics dictates that systems naturally evolve towards greater disorder. A vibrating crystal will eventually dissipate its energy and stop. But this ytterbium crystal continued to oscillate indefinitely, a tiny, isolated system stubbornly maintaining a regular rhythm. It's as if the crystal had built its own little clock, ticking away without needing to be powered. Importantly, the oscillations aren't simply random fluctuations. They are precisely timed, repeating, and synchronized. This precision is what distinguishes a time crystal from a chaotic system. While a chaotic system might exhibit some degree of periodicity, it's ultimately unpredictable and unstable. A time crystal, however, displays a truly robust, self-sustaining rhythm. The implications of this discovery are far-reaching. It suggests that the very fabric of space-time might be more flexible than we previously thought. It challenges our fundamental assumptions about the nature of time itself. Physicists are now exploring whether similar time crystals could exist in other materials, perhaps even in more complex systems like molecules or even larger, macroscopic objects. The current time crystals are incredibly delicate and require extremely low temperatures, colder than outer space, to maintain their stability. However, researchers are actively working on ways to create more robust and practical time crystals. One avenue of research involves exploring different materials and geometries to enhance their stability and simplify their creation. Another exciting area of investigation involves the potential applications of time crystals. While still in the early stages of development, the unique properties of these crystals could eventually be harnessed for a variety of technologies. Some potential applications include ultra-precise sensors, which could be used to measure time with unprecedented accuracy. Other possibilities include novel types of quantum computers, where the self-sustaining rhythms of time crystals could be used to perform complex calculations. The study of time crystals isn't just about understanding a new phase of matter. It's about fundamentally rethinking our understanding of time itself. It forces us to consider whether time is merely a linear progression, or if it's something far more complex and potentially malleable. The existence of these self-oscillating crystals provides a tangible example of a system that appears to exist outside the conventional flow of time, hinting at possibilities that were once relegated to the realm of science fiction. It's a reminder that the universe holds secrets that continue to challenge our perceptions and push the boundaries of scientific understanding. As research continues, we can anticipate even more astonishing discoveries and a deeper appreciation for the intricate and often surprising nature of reality. Consider subscribing and sharing these moments with those who seek peaceful understanding. The dance of quantum realities now settles, allowing your mind to quiet, to uncoil, and simply be. Let your thoughts gently unfurl, drifting away with the night's embrace.